Assalamu alaikum class. I hope that all of you are well and safe in your homes inshallah. Lecture 41 and 42 of our course Signals and Systems is the concluding lecture for the course. So for this lecture we'll start by a summary of the Fourier analysis techniques. Later on I'll introduce you some frequency domain terms relevant to Fourier analysis. So we'll define certain concepts which are derived from these Fourier techniques. We'll conclude the lecture by seeing sampling from a frequency domain perspective. You remember that sampling is a process which converts an analog signal to a discrete signal. So this analog to discrete conversion is an interface to processing of signals by digital computers. So we'll see how can we observe sampling from a frequency domain perspective, as well as when we are outputting the signal from the computer, say. So there's a reconstruction. The signal has to be converted into the analog domain. So reconstruction of the signal from the discrete to analog domain is done through a process known as reconstruction. So we'll be seeing the process of reconstruction from a frequency domain perspective too. Starting from lecture 27 to lecture 41, we had studied the Fourier family of techniques. We saw that Fourier analysis is a method to observe the frequency content of a signal. We also saw that if we plot the magnitude of that frequency content versus omega, the frequency, then it is known as a magnitude spectrum. And if we plot the phase of the frequency content versus frequency, it is known as a phase spectrum. We also saw that for a real signal, as we'll be encountering in our course, the magnitude spectrum is even symmetric and the phase spectrum is odd symmetric. So given in front of you on the slide is a summary of the Fourier analysis technique, or you can say a summary of how the spectrum looks like for a particular type of a signal. We remember that for periodic signals we used the Fourier series, and in case of Fourier series the spectrum was discrete. That is why it was termed as a line spectrum. Whereas for aperiodic signals we used the Fourier transform, and the spectrum in case of Fourier transform was continuous. That is, it existed at all frequencies. In addition to these broad definitions, we'll see individually how the spectrum looks like. It is also important to mention that Fourier transform is a more general type of technique because it can be used to analyze both periodic and aperiodic signals. Also, when you will be studying the subject digital signal processing in your future courses, you will see that all these techniques converge to a method known as discrete Fourier transform for use in computers these days. So, if the input signal is continuous and periodic, then for Fourier series, the spectrum is discrete and aperiodic. The spacing between the spectrum is an integer multiple of the period of the signal. If the signal is discrete and periodic, that is, it is a discrete time signal, then the spectrum is also discrete and periodic. If the signal is continuous and periodic and aperiodic, then its Fourier transform is taken, and the spectrum of Fourier transform is also continuous and aperiodic for a continuous time signal. For a discrete time signal, the spectrum is, if the signal is aperiodic, the spectrum is continuous and periodic. So the spectrum for discrete time signals is always periodic because of the periodicity of the complex exponential. If we observe, we see that both a discrete time Fourier series and continuous time Fourier transform, the time domain and frequency domain signals have the same features. If it is continuous and aperiodic in one domain, it is continuous and aperiodic in the other domain. If it is discrete and periodic in one domain, it is discrete and periodic in the other domain. So for both these signals, duality existed. That is, a signal from the one domain could be converted into other by a simple duality theorem. Whereas for continuous time Fourier series and discrete time Fourier transform, the characteristics of the time domain and frequency domain signal are not the same. However, if we observe continuous time Fourier series and discrete time Fourier transform, we can see that there is a duality in these two types of techniques. So that is why in the last lecture we stated that a duality between these two signals can or these two types can exist. These two type of transformations can exist. As we just discussed, that Fourier analysis is capable of giving us a magnitude spectrum and a phase spectrum, and for real signals the magnitude spectrum is even symmetric and the phase spectrum is odd symmetric. Now in many cases when we are analyzing systems, we want to see the system's frequency response for a wide range of frequencies. Especially in the case of continuous time Fourier transform, if we want to observe the frequency response of the system, we have to vary the frequency from 0 to as high as we could get. So it is difficult to observe such a wide range of frequencies in one graph. So the easier or the simpler option is to convert that linear frequency scale into a logarithmic scale. And then as we know that in logarithms the values are compressed or the scale is compressed so that we can observe a wider range over a smaller physical as you could say axis. So smaller apparently physical axis is capable of providing us a wider range of parametric variation. Generally for continuous time Fourier transform, that is why Bode plots are used where frequency axis is especially logarithmic, and in MATLAB or other software you'll see that they also compress the magnitude axis because it's easy to compress the magnitude axis as well, and it gives you an better view. So Bode plot is a technique where you will be plotting the magnitude versus frequency or the phase versus frequency on a logarithmic scale. Generally for discrete time, we need to plot between 0 to omega because as we discussed, discrete time spectra are periodic with a period of 0 to 2 pi, but the plot from pi to 2 pi is a mirror image of the plot from 0 to pi because magnitude is even symmetric. Sometimes especially when we are using computer algorithms for discrete time systems too, the Bode plot is used to observe the response. So what happens is when we are determining a Bode plot is that we multiply the hg omega or the magnitude response by 20 after taking the logarithm. So you can say that it is 20 into log 10 of magnitude, or in case you are given powers, it is 10 into log 10 of power. Both of these plots are the same. So when magnitude is 1, the logarithmic value is equal to 0 dB. When the magnitude is under root 2, the logarithmic value is 3 dB, and so forth. Why we use decibels? Because conventionally decibels have been used since long to plot such kind of plots. I have mentioned a reference at the end to see where and why and who devised those plots, and as we can guess, Bode plots are named after a scientist known as Bode. His name was actually Hendrik Wade Bode. On the slide is a typical Bode plot for a second order system. We can see that the magnitude variation is say from 0 dB to 50. although it's minus 50, but let's say the magnitude varies by 50 units. So a magnitude variation of 50 units means that it's around a variation of 350 values. Similarly, along the frequency axis, you see that the frequency varies from 0 to 1000, and this large variations are mapped into a very small space on the graph. Now this magnitude is negative because whenever we take h of j omega as a transfer function, we know that it has a numerator term and the denominator term. And the composition of logarithms is such that the denominator term gets subtracted from the log of the denominator term gets subtracted from the log of the numerator term. So this means that the denominator was that the magnitude of the denominator was more than the magnitude of the numerator. That is why, as a result, the result was negative. Similarly, a typical Bode plot for a second order discrete time system is shown in figure, and we can see that the plot from 0 to pi is the same as the plot from pi to 2 pi. It's a mirror image, or the mirror is taken along the x-axis, or you can say that the mirror is taken along the x-axis from minus pi to 0. So we see the advantage of Bode plots is that the scales are compressed and we can observe a larger variation over a smaller space. Shown on this slide is a MATLAB example for plotting Bode plots. The example is self-explanatory. I leave it to you to use this example and draw the Bode plots and see what happens, what kind of a response this is. Also derived from the concept of frequency spectrum determined from the Fourier series are two important terms known as the energy density spectrum, or the ESD, and the power density spectrum, or the PSD. These terms are derived from Parseval's relation, which say that for an aperiodic signal, the signal energy determined from the time domain is the same as the signal energy determined from the frequency spectrum, or the Parseval's relation equates the signal energy between the time and frequency domain to an expression. Similarly, if we have a periodic signal and we determine signal power, it is the same as the signal power determined from the frequency domain perspective. Now we have already studied the concept of energy density spectrum in lecture 34, which says that this magnitude x of j omega whole square is describing how the energy, signal energy, is distributed versus the spectrum versus the frequencies omega. Therefore, it is known as energy density spectrum. Similarly, for a power signal, the distribution of magnitude ak square, where ak are the Fourier coefficients and exist for only discrete values of k. This describes the distribution of power as a function of frequency, and it is known as the power density spectrum of the periodic signal. So sometimes in your communication courses, you will be plotting the magnitude density spectrum, the energy density spectrum ESD or the PSD versus frequency omega. So how a typical ESD curve would look like is going to be illustrated on this slide. Shown on the slide is a typical gate function or a pulse, and this is the Fourier transform, which is a sinc function. I am sure by this point you are very well aware of how to determine the zero crossings of the sinc function. So when we take the ESD or the energy spectral density, since the magnitude square of f omega is taken, so all the negative values also come positive, and because of the squaring, the peaks and troughs are more pronounced now. If this spectrum is a two-sided spectrum, that is, it extends from negative frequency to omega frequency. If we consider that the magnitude spectrum is even symmetric, so we can take single-sided EST, which is provides us with the same information as a two-sided EST. So it will look like this curve, whereas the energy between 2 points omega 1 and an omega 2, two frequencies, is shown shaded in the figure. So from all the frequency domain features that we have discussed so far, we can classify a signal with respect to frequency, just as we have classified signals with respect to time in our initial lectures, lecture 1, 2. So for an energy or a power signal, if its ESD or PSD is such that it is concentrated around the zero frequency, such a signal is known as a low frequency signal, such as the signal shown in the adjacent figure. We can see that this time domain signal for this x of j omega must be a aperiodic signal because the spectrum is continuous. So this is ESD, and now this ESD or x of j omega is such that its concentration is more towards zero frequencies, and as frequencies will increase, its value will decrease. So such a signal is called a low frequency signal. Shown on the right is for a discrete time case, and again pi represents higher frequencies and 0 represents the lower frequencies. Similarly, if the spectrum is such that the energy is concentrated towards higher frequencies, then such a signal is known as a high frequency signal, such as the one shown in the figure, where for 0 or around 0, the magnitude of the frequency response is low, and as you go towards higher frequencies or as the frequency increases, the magnitude gives higher values. This is also clear from the discrete time plot shown in the figure. If the signal has a spectrum which is in the middle range, not towards the high frequencies or towards the low frequencies, then it is known as a medium frequency signal or a band pass signal as shown in the figure. Now the signal spectrum is such that the ESD is concentrated around a middle range of frequencies. Now I have given these definition in terms of ESD and PSD because this is how the frequencies are defined, or these are how the signals are classified. But it is okay if you identify the signal through the magnitude spectrum only and not the ESD plot, because you know that the ESD plot is essentially conveying the same information as the magnitude spectrum. It is just a more enhanced version of the plot as we saw in the example on the previous slide. For communication systems, it is often required to describe the bandwidth of a signal. There is no fixed definition to define the bandwidth of a signal, so we will be considering two definitions today. The first definition pertains to defining a range of frequencies where a certain percentage of signal energy or power is concentrated. For example, we can say that if a continuous time signal has a 95% of its PSD or ESD concentrated in the frequency range between F1 and F2, then the 95% bandwidth of the signal is F2 minus F1. Similarly, we can define 75%, 90% or 99% bandwidth of the signal. The second definition of bandwidth is what is more commonly used to define filters is the 3 decibel bandwidth or 3 dB bandwidth. It is defined as the difference between frequencies at which the h omega or the magnitude drops to a value equal to 1 by under root 2 times the peak value. So that if you take the logarithm of that value, it comes 3 if the peak value was 1. 3 dB bandwidth is also known as half power bandwidth because the voltage of current attenuation at 3 dB is equivalent to a power attenuation by a factor of 2 because it is equal to 1 by under root 2 square, which is 1 by 2. So shown on the figure is a situation where 3 dB bandwidth is shown for a low pass filter, and for the filter on the right 3 dB bandwidth is shown for a band pass filter. So you can see that for a low pass filter it was from 0 to omega naught. On one side it was omega naught, the bandwidth, and for the band pass filter 3 dB bandwidth is W2 or omega 2 minus omega 1. More frequency domain definitions. We have the frequency terms narrowband, wideband, and ultra-wideband signals or filters. So these terms are described for a low pass or a band pass signal or filter. The term narrowband is defined, or these terms basically are defined by the ratio of bandwidth at minus 10 dB to center frequency. So the minus 10 dB point is the point which is 10 dB lower than the peak power. The center frequency for a low pass filter is 0, and for a band pass filter would be any frequency. So in this context, the fractional bandwidth is defined as the ratio of signal bandwidth to center frequency, which is 2 cross FH minus FL divided by FH plus FL, where FH is the higher frequency and FL is the lower frequency. So a narrowband filter will be one whose fractional bandwidth is less than 1%. A wideband filter is one where the fractional bandwidth varies between 1 to 20%, and an ultra-wideband signal or filter is one whose bandwidth is fractional bandwidth is greater than 20%. In this figure you can see this clearly, and you can also see that the frequencies are plotted against the power spectral density or the ESD to define what kind of bandwidth this filter occupies. We have discussed band limited signals once in our course. So what is a band limited signal? A band limited signal is one whose spectrum is 0 outside a certain frequency range. For example, if a signal is band limited to B Hertz, then the spectrum will be 0 beyond B Hertz of frequency. Now you'll see that I have been using omega and F interchangeably because both of them represent frequency, and the relationship between omega and F is omega is equal to 2 pi F. So when we were doing Fourier series, we saw how can the spectrum be plotted versus F or omega. In a similar fashion, the spectrum x of j omega for Fourier transform can be plotted against frequency F as well. But the point is the spectrum does not exist beyond a certain frequency is when the signal is band limited till that frequency. For a discrete time signal, the signal is periodically band limited if the frequency spectrum is 0 for omega naught to pi variation of frequency omega. Now for discrete time spectra, we know that the frequency response is expressed in a slightly different way, and that is because the spectrum are periodic. So the spectrum is non-zero till frequency omega naught. In that case, the signal is band limited to omega naught hertz. This is represented in this figure. For a discrete time aperiodic signal, the Fourier transform was band limited to omega naught hertz. Similarly, for a periodic signal like this, it was band limited to m2 pi by n, and you can see what discrete frequency it represents. Enough of the frequency domain definitions. Now we are going to see how the frequency domain characterization of signals and systems simplifies some mathematical processes for us. So the process that we are going to consider is analog to digital conversion. In analog to digital conversion, the first step usually is sampling of the continuous time signal or sampling of the analog signal into a discrete time signal. What happens during sampling is that the values of signal are obtained at discrete intervals of time, but the values are continuous and they can take any amplitude. After sampling, the values are quantized, that is, they are assigned a certain set of amplitudes and we obtain a digital signal. The sampling and quantization process is interchangeable, so it can be done that first we quantize and then we sample, but our focus is just the sampling process. From the following slide, we'll see how the sampling process can be visualized through using Fourier analysis techniques. The concept of sampling in the time domain can be visualized as multiplying the input signal x of t by an impulse train p of t. So after multiplication, we get our pulsed input or the sampled input xp of t, which is a product of the input x of t and the pulse train p of t. This impulse train can be visualized as continuing from minus infinity to plus infinity. Del t is t minus n of t, where t is the sampling time, or it is the inverse of the sampling frequency fs. So after the multiplication, the sampled signal xp of t is x nt multiplied by del of nt. What happens can be observed graphically as, if this is our input signal x of t, after multiplication by the impulse train separated by capital T, we get this pulsed signal or the sampled signal. Each of the samples are separated by this interval t. It is seen that after sampling, the amplitude of this impulse train is modified such as the envelope or the periphery of the amplitude is giving us information about the input signal x of t. This sampled signal is the same signal as was shown in the last slide. So the sampling process is, in the time domain, a product of the input signal with an impulse train. What happens in the frequency domain, we'll see on the next slide. Now in the time domain, the product of the input signal with the impulse train is written as x of nt del of t minus nt as a consequence of the sampling property, which says that whenever a function is multiplied by an impulse, as a result we get the same impulse, but now the magnitude of the impulse is modified as per the amplitude of the signal by which it was multiplied. So x of nt represents the value of the input signal xt at that particular instant of time. Now in the time domain, our signals are being multiplied. What happens in the frequency domain is that convolution in time is multiplication in frequency, and vice versa. By duality, multiplication in time is convolution in frequency. So if we are to take the Fourier transform of this sampled signal, it is actually the convolution of the spectrum of the input signal x of j theta and that of the pulse train p of j omega minus theta, where this expression is just representing that this signal is flipped and slided and this signal remains as such. Now when we take the Fourier transform of an impulse train, we'll come to see that the Fourier transform of an impulse train is an impulse train. So when we convolve our input with this impulse train, we remember from our knowledge of impulses that when we convolve a function with an impulse, we get the function at the location which is defined by the impulse. That is, if a function x of t is convolved by an impulse del of t plus 1, the spectrum of the signal is shifted at t is equal to minus 1, which is the instant at which the impulse occurred. So if we convolve the signal by this impulse train, we'll get a train of signals occurring simultaneously. So let's see what happened with the frequency spectrum. Say that our signal x of j omega was band limited such that the maximum frequency it possessed was omega m. This is our impulse train which is sampled at a frequency omega s. So when you convolve both of these, the first, because of this impulse, let me choose a pen. Okay. So because of this impulse, when this impulse convolves with this function, we get this portion of the spectrum. Similarly, when this impulse, the impulse occurring at omega s, convolves with this function, we get this copy of the signal. Now, the signal instead of 0 appears at omega s. Similarly, let's say we take this impulse. This impulse represents del of omega plus omega s. So now when this impulse convolves with the function, we get this version of the signal. So what happens in the frequency domain is when the signal is sampled, the transform of the sampled signal is multiple images, multiple replica of the same signal. Now each of these signals is separated from its replica by a frequency with this one. If this was omega m and this is omega s, then this edge represents omega s minus omega m, because this edge was omega m. So when this spectrum is shifted to a frequency omega s, then after shift, say let's shift the spectrum to a frequency omega s. So after shift, the 0 point becomes omega s, the plus omega m point becomes omega s plus omega m, omega s plus omega m. Excuse my drawing class. And this point becomes omega s minus omega m. Okay, omega m is clear. So this end is omega s minus omega m. And we can see that as long as omega m is less than omega s minus omega m, the spectrum does not overlap. What happens if omega s minus omega m is not less than omega s minus omega m? So what happens? Let's see. What happens if omega s is greater than omega s minus omega m? Or in words, since omega s is representing the sampling frequency and omega m is representing the maximum frequency possessed by the signal, what happens if the difference of sampling frequency minus maximum frequency of the signal is less than the sampling frequency? Well, this is what happens. There is spectral overlap, also known as aliasing. The spectrum is damaged. As a result, if we try to reconstruct this signal by, say, using a low pass filter, it is not possible because the spectrum is permanently damaged and there is no way that we can recover the original signal. So for no spectral overlap or no aliasing, we must have omega m less than omega s minus omega m. And if we simplify this relationship, we have the sampling frequency should be greater than twice the maximum frequency of the signal, which is a very important theorem in communication systems. So if omega is greater than 2 omega m, x of t can be recovered from the sampled version by means of a low pass filter with gain t. Now the gain of the low pass filter would be t, because we see that the sampled signal had a magnitude of 1 by t. So when we multiply the magnitude 1 by t, we'll get a magnitude of 1, so the original signal will be recovered. So this result is referred to as the sampling theorem, and it can be stated as: if xt is a band limited signal with x of j omega 0 for omega greater than omega n, then xt can be uniquely determined by its samples if omega s, sampling frequency, is greater than twice the maximum frequency of the signal, or omega s is greater than 2 pi by t. So given these samples, we can reconstruct x of t by generating a periodic impulse stream in which successive impulses have amplitudes that are successive sample values, or in other words, we are doing impulse stream sampling. To reconstruct the signal, we'll pass the signal through an ideal low pass filter with gain t and cutoff frequency greater than omega m, and less than the other before the other sample comes, omega s minus omega m. So the resulting signal will be exactly equal to x of t. Now we know how to sample a signal and at which frequency should a signal be sampled in order for it to be reconstructed properly. This was a sampling theorem, or this was the theorem which I said there is a certain rule which says that as long as we are sampling at a certain frequency, we are sure that we are going to get our original analog signal back. So this sampling theorem is the basic theorem which was not named but which was talked about then. This is a very important theorem, a very important concept for communication systems. So to reconstruct the signal xp of t, we'll pass this signal through a low pass filter to get our original signal xrt back, or the reconstructed signal xrt is going to be the same as x of t. Now whenever a signal passes through a filter, a time domain signal passes through a filter, in time domain convolution takes place. So I'm not going to go into detail how the convolved signal looks like in the time domain, because we are simplifying our process through the frequency domain representation. So convolution in time is multiplication in frequency. So what happens in the frequency domain is that both of these responses, xp of j omega and h of j omega, will multiply by each other. We already discussed that to cancel the 1 by t gain of the xp j omega, we have to get a gain of t, give a gain of t to the filter. So we have a filter which is defined between the frequencies minus omega c to omega c, such that the cutoff frequency omega c of the filter varies between omega m to the replica, other version of the signal, omega s minus omega m. So it could be anywhere in between these two frequencies. This is the input signal. The xp of j omega, or the input signal to the filter. So now once this signal, this spectrum is multiplied by this, we'll only get the lobe where our main or center portion of the spectrum exists. We can say that the filter is, say, between this range. So this is omega c and this is minus omega c. So what happens is, when these two responses get multiplied, we get xr of j omega. And if we take the time inverse transform of xr of j omega, because xr of j omega is the same as x of j omega, which is the original spectrum, so xr of t is going to be the same as x of t. So as long as sampling theorem is ensured, the sampling frequency is greater than twice the maximum frequency of the signal, and we choose a filter with a cutoff frequency omega c, which is between omega m and omega s minus omega m, we can ensure that our original signal is recovered, and this reconstruction process takes place when we are going to perform the digital to analog conversion. So I hope that you are clear with the sampling process now. We are just going to discuss this sampling and reconstruction process briefly, and that too from a frequency domain perspective. when you will be studying communication systems and DSP, you will be doing this process in much more detail. But it's important to relate it with what we have learned so far. So in today's lecture, we have seen some frequency domain concepts. So it is important for you to learn those concepts. I might ask you what is the bandwidth of a signal if a signal is visible in front of you, or what is a narrowband signal, whether the following signal is a narrowband signal or a wideband signal. So for you it is important to know those concepts and try practicing them yourself. For example, practice problems, we are going to discuss the sampling theorem only. Now this first example is problem 7.2 of your book, which asks you to see whether the chosen sampling time or the chosen time of the impulse train is sufficient for us to reproduce the signal. So we have an ideal low pass filter with a cutoff frequency omega c is equal to 1000 pi. If impulse train sampling is performed, which of the following sampling periods would guarantee that xt can be recovered? We are not given any information about the signal, so we can say that we are sure that the sampling time is such that the signal would be sampled okay. We are just concerned about the endpoint, which is the filter. So omega c is 1000 pi. Now we know that the cutoff frequency of the filter is such that it varies between omega m to omega m minus omega, or to omega s minus omega m. So the lowest point of the cutoff frequency is omega m, or we can say that omega m is equal to 1000 pi. Now we know that the sampling frequency is greater than 2 omega m. Since omega m is 1000 pi, so omega s is greater than equal to 2000 pi. So if the sampling frequency is greater than 2000 pi, then the sampling time should be less than 1 into 10 to the power minus 3. Why should it be less than this? Because we know that time and frequency have inverse relationship. So as the sampling frequency increases, the sampling time decreases. If, however, the sampling time increases, the sampling frequency decreases. So the sampling time should be less than 1 into 10 to the power minus 3 for us to be sure that the signal is reconstructed properly. Now for signal A, the time, the sampling pulse train sampling time is 0.5 into 10 to the power minus 3, which is less than 1 into 10 to the power minus 3. So we are sure that with A sampling period, we can reconstruct our signal. For B sampling period, since this time is greater than this time, Ts, so our signal cannot be reconstructed. And similarly, since 10 to the power minus 4 is also less than 1 into 10 to the power minus 3, so we can say that if we are using a impulse train with a sampling time equal to 10 to the power minus 4 second, then our signal can be reconstructed correctly. So this simple question concludes. The next problem is problem 7.21 of your textbook. Here we have to see that whether the given constraints are sufficient to guarantee that xt can be recovered from xp of t. So we have a impulse train sampling, and the time period of the impulse is 10 to the power minus 4 second. So the sampled signal has samples after every 10 to the power minus 4 seconds. Now for the first signal, we are given that the signal is band limited and the maximum frequency is 5000 pi. The maximum frequency of the signal is 5000 pi. Beyond 5000 pi, the signal is 0. For the second signal, the signal is band limited and the frequency band, or the maximum frequency of the signal, omega m, is 15,000 pi. For the third signal, we are just given that real of x of g omega 0 for omega is greater than 5000 pi, which means that the real part of the signal is band limited to 5000 pi hertz, we are given no information about the imaginary part of the signal. In these cases, you can argue that we are given no information, but this is x of j omega, which means that it includes information about both real and imaginary parts. But for this question, we have no information about the imaginary part. So let's solve these questions. For the first part, the maximum frequency of the signal is 5000 pi. The sampling frequency should be greater than twice the maximum frequency of the signal, which comes out to be 10,000 pi. Now, as we discussed for the previous numerical, the time, the maximum sampling time is 2 pi by omega s, which is 2 into 10 to the power minus 4 second. So as long as our sampling frequency is greater than this frequency, or the given sampling time is less than this T max, our signal can be recovered. We were given a sample time of 1 into 10 to the power minus 4 in this question. Since this time is less than T max, therefore our signal can be recovered. For the second part, we'll proceed in a similar way, and for this case, our maximum sampling time is 6.66 into 10 to the power minus 5 second. Now this sampling time is not less than the given sampling time. In fact, the given sampling time is greater than this time. If it was less, then the signal could have been recovered, but since it is greater, so the signal cannot be recovered. For the third part, since we already discussed that imaginary x of j omega is not specified and there is no additional information given about it, or x of t, so we can say that recovering of xt cannot be guaranteed. So this brings us to the end of our lecture and the end of our course, alhamdulillah. For this lecture, you have to go through the definitions taught in the lecture and solve problem 5.27, 7.2, 7.3, 7.21 and 2.2 of our textbook. Two of these problems have already been discussed in the lecture. I wish you good luck for your studies. In case you have any trouble in today's lecture or all over the course, through the entire course, you're most welcome to text me, email me, message me, and I'll be responding to you. All the best. Allah Hafiz.